The subject of today's lecture is standing waves and phasor signal diagrams. Now, I think most of you are probably glad to get away from the study of reflections, and especially all the difficult problems that you had to work. However, today you're going to find that you'll put those in actual use in studying phasor signals, so that you'll see that the study of reflection was very worthwhile. So we'll start then with a new phase of the session, which now deals with sinusoidal signals, and of course we're going to look at standing waves and see how they're generated and what happens. So the first statement I'd like to make to you is that standing waves are caused by two signals of the same frequency traveling in opposite directions on a transmission line. That's the way you develop standing waves. To get these two signals, usually it's going to be because of a reflection. However, there are situations where you have leakage signals in the system. It looks exactly like a reflection, and you'll have the same effects in the overall system. Now let's look at this line here. Here we have a signal traveling at the velocity of light. This dotted line out to the right shows where this wave would have gone if you didn't have something in here to stop it. In other words, this wave would have gone out here at the speed of light. This negative half wave here, positive, negative. But at this point, we put a short circuit. We prevent this wave from going to the right. So instead of going to the right at the velocity of light, it's going to go back to the left at the velocity of light. But we know that at a short circuit, that if you have a voltage wave coming in, you know that it's going to reflect and be exactly 180 degrees out of phase. Well, let's see the effects of this at a function of time. If you could stop this wave, if we could stop this wave exactly the way we see it here, you can see that this incident sine wave here that's the incident sine wave there, in here, going in this direction. This wave did not go out to the right. Instead, it goes back in this direction, and it's indicated by this arrow and this arrow here. In other words, this wave, where you have the little phasors up like this, the little vectors drawn up like this, the electric field, or the voltage, this is the wave that's traveling in this direction. This sinusoidal envelope here is the one that's going to the right. Now let's look at this then as a function of time and see what happens. I'll take this to draw these little lines here, 30 degrees, 60 degrees, 90, and so forth. I'll draw them sort of agreeing with what you have on the other side. Now we can look at this from the standpoint of each one of these little vectors. Here's your sinusoidal wave as it would have gone if it had gone to the right. Let's take this one right here. Instead of going to the right 30 degrees, it hit this surface here, which is a short circuit, was reflected out of phase, and went back here 30 degrees this direction. The next one, instead of being negative here, it is positive over here, going in this direction at the speed of light. This one, instead of traveling 90 degrees over here, it travels 90 degrees this way, and it is positive instead of negative. I think you can look at this and go to the next one over here. You have 180 plus 90 for this one right here. 180 plus 90. However, this was plus, but when it hit this short circuit, it reflected out of phase, so it's negative here. Now, if you study each one of these, you have 180 plus 180 plus 90. This was negative. 180, 180 plus 90, and it's positive. So we stop this wave at this instant in time and say, what is the resultant? Well, you wouldn't even see any of this. You wouldn't see this. You wouldn't see this. You would see the resultant. You would see this added to this one, this added. So at this point, you have 2e. The resultant value is 2e here. Over here, you would have 2e. Here, we'd have a negative 2e. That's the waveform you would see if you could stop it at this point. You would see this waveform here. If you could stop and see the overall waveform that exists. That's what's on the line at this particular instant in time. It should be very clear that's what's happening. This wave is traveling to the right at the speed of light. This one is traveling, it would have gone out here, but instead it's going back here. At this point in time, if you stop this overall envelope here exactly matches this folded over here, this folded over here, and this folded up here, such that when you take the resultant, you have this waveform. Now let's look at this waveform. When this point here moves to the right 90 degrees, this is moving to the right 90 degrees. In other words, this sinusoidal waveform here has moved to the right at the speed of light only 90 degrees. Now look at the fold over. I'll draw these in terms of just, might as well make it the way we had it here. This is easy to see. Take this one here. Instead of going 30 to the right, it hit this short circuit, reflected out of phase, and it went over here. So instead of being over here, this signal is over here. Take this one, 90 plus 90, which is this number 3 line, this line right here. So we have here 90 plus 90. But instead of being negative over here in this phase here, when it hit the short circuit, it was reflected positive and traveled back here, so it is positive here. So this point here, which would have gone out here, has actually traveled back here, and it is positive in this direction. Take another one, 90 plus 180 plus 90, and it's positive here. But we know that if we go 90 plus 180 plus another 90, but instead of being positive over here, it is negative here, because when it hit the short circuit, it was reflected 180 degrees out of phase. Now look at this. If you stop at this point then, and you could look at everything on the line, you can see that at this point, you know the voltage is always 0 here. So here you have an incident wave here, and you have a reflected wave here. The two of them have to add up to 0. So you'd have this like this. You'd have the negative here, and of course that's 0. I think all of you see that if you look at this and add all of these up, that the resultant here is 0 all along this line. Because this is exactly the negative value that cancels this. This positive value and this positive value are equal, they cancel. So at all points along this transmission line then, all of these cancel. The reflected, this is traveling in this direction, this is traveling, this wave is traveling in this direction. At that instant in time, all of these cancel, and you have 0 voltage at all points on that transmission line. How fast is this traveling? The speed of light, and it has only traveled 90 degrees. Now look what happens when you travel another 90 degrees. Now this point travels on over here, another 90 degrees. Total 90 plus 90, this has traveled 180 degrees to the right. This waveform here has now traveled to the right 180 degrees. Now I think you can see that it was negative here, it's positive here. This has traveled exactly 180 degrees. Now look what happens here. To make it very simple and agree with what we did before, I'm going to only draw these waveforms here to show the major points of interest. Instead of traveling to the right 30 degrees, the wave traveled to the left 30 degrees. Instead of being positive like this, it is negative because it reversed the phase at the short circuit. The next one, instead of going over here 60 degrees, it went over here 60 degrees. It's negative instead of positive. The same thing happened. Instead of going to the right 90 degrees here, past the interface, it hit the interface and went back this direction, and it's negative instead of positive here, again because it reflects 180 degrees out of phase at a short circuit. Okay? Now look at this point here. 180 plus 90. 180 plus 90. This point here. But instead of being negative, we know that it reflected out of phase So it's from negative, it's reflected positive, and it's going in this direction, speed of light. So you have now, again, two waves. This wave up here, the envelope traveling to the right, and the other that's represented by these little lines here is traveling to the left. Now at this instant in time, if you add all this up, this adds to this adds to this adds to 2e, minus 2e, this is plus 2e, and again, minus 2e down here. That's the waveform. Now notice how far this wave has traveled. The wave has traveled to the right 180 degrees. Look what happened here. This went from a positive all the way up like this and reversed. Now you have this situation here. So this waveform here decreases to 0 here. Then it decreases negative here, and you have this wave doing this. Now if you look at this as a function of time, you can see it started here. The two waves went like this. It's only traveled 180 degrees. 270 degrees, it's back to 0 and back to here. In other words, from this point, when you go back and up here, you can see that, in other words, look at this as though this were on down in this direction here. As this goes back another 90 degrees to the right, over here, this waveform is going to collapse and go back to 0 like this. Then the next 90 degrees, this is going to go from 0, and the waveform will go up here, and you'll return to this point here. So just look at it as coming down and back up. Down 30, 180, back up 270, plus 90 is 360. So when you've gone 360, notice what you have done. This goes from here, 90 degrees, 90 degrees, 90 degrees, 90 degrees. 4 times. 360 degrees. So by the time this wave travels to the right, 360 degrees, this waveform has gone from this position here and back up to here. Now, this wave is going at the speed of light. What do you see here, if you could see it? You just see this standing here going up and down. A standing wave. That's how the pattern is generated. I've shown it for the maximum reflection. If there were just a small reflection, it would be a totally different looking wave, and we can show that later. But you can see what's happening. This wave is just standing here doing this. This is the voltage wave. What's the current wave doing? What's the current wave doing? Over here, current. Notice, when the voltage is 0 here, the current's maximum, isn't it? So you can see that this waveform here is going to be oscillating back and forth. And if you drew that on here, you can see it would look like this. I drew it a little bit wrong here. This is a 0 at this point here, 0 at this point here. It'd be a maximum down here and back to 0 here. So that this waveform here is the current waveform. You can see it's maximum here, where the voltage is minimum. When this is minimum, the voltage will be maximum. And that's exactly the way this is going to work. When the voltage is up here, the current is going to be minimum. So you can see then that these two waveforms are just sitting here going up and down. But notice that the voltage and current are always 90 degrees apart. 90 degrees apart. Any question about any part of this so far? You see how a standing wave is generated now? Any problem? Any question? Very simple, isn't it? If you could stop it here and look at this, this wave here is folded over here, this is folded over here, this is folded over here, because this, instead of traveling to the right this far, has traveled to the left this far. It's positive, meeting it with the positive wave going into the right. This is going to the right, maximum positive. This is going to the left, maximum positive. Adds up to 2e at that point. When the wave travels to the right, then 90 degrees, this collapses from here all the back to 0. So now you have 0 voltage at all points on the transmission line. When it travels to the right another 90 degrees, then it goes from 0 to this point. Okay? Then the next 90 degrees, it goes back to 0. The next 90 degrees, it goes back to this position here. So when the wave travels to the right 360 degrees, this waveform goes 90, 180, 270, 360. And it just keeps doing that, standing there. A standing wave of voltage. The current is exactly 90 degrees from that, because when the voltage is maximum, the current is 0. When the current is maximum, the voltage is 0. But this is the waveform that you would see. As a function of time, both of these are varying. And this is the kind of waveform that you would see. That's called a standing wave pattern. Now, do you see this? Is it normally drawn like this? Most textbooks, when you see this drawn, you will see a waveform like this. Looks like I kept that out a little too long. If this is a short circuit here, the voltage is 0, you get this waveform like this. Why do you get that waveform? Because you're detecting this with some type of detector, crystal detector. Now, can the crystal detector catch this at this instant of time, or this instant of time, or any other instant of time? No, when this goes across here, you are seeing this wave going up and down like this, and you're detecting this amplitude here. When you move the probe over here, you're getting this amplitude here. When you move it on further over, you get another amplitude. Now that's what happens then on the transmission line. Usually, as you know, you see this drawn the way it's drawn here. Now the current would be like this. That's the current. That is the voltage. Notice, when you have maximum current, minimum voltage. When you have maximum voltage, what do you have? Minimum current. Now, in the study of reflections, you found out something very definite about a pure resistance load. What happened when the electric field went out and hit the short circuit? Reflects 180 degrees out of phase, right? What happened when the electric field came out and hit an open circuit? The reflected wave, instead of reversing, it went up to 2E, didn't it? At the open circuit. Now look at this. This is 2E. This is 0. What's the impedance at that point? You have a voltage, but you have no current. The total impedance must be infinite. Isn't that what an open circuit looks like? We showed that for the DC case with a battery. We know then that at this point the incident voltage plus the reflected voltage, E sub I, plus E sub R, gave us 2E sub I, didn't it? The voltages add up to 2E, but the current is 0. So the impedance is infinite. It's like an open circuit, isn't it? Over here, what did you have? You had maximum current, minimum voltage. That then is a short circuit. 0 resistance. But notice something that we found out when we studied reflections. If there's any impedance that is a pure resistance greater than Z0, what happens to the wave when it comes along and hits this pure resistance value that's greater than Z sub 0? The voltage always goes up, doesn't it? Pure resistance. What happens then if you have a resistance that is a pure resistance less than Z0? What happens to the voltage now? The voltage comes along the line, but instead of going up, the voltage has to go down because the resistance is smaller than Z0. It can't support that voltage. So the current goes up and the voltage goes down. Notice if it's a pure resistance, it will go exactly in phase, won't it? Notice this. This is exactly in phase. This is exactly out of phase. Exactly out of phase, exactly in phase. If you looked at this then from the standpoint of resistance, you know that this point has to be a pure resistance value because the two are in series, in phase, aren't they? Two signals are in phase. It has to be this situation here. What has to happen over here? This also has to be a pure resistance, doesn't it? In this case, it's zero resistance, but it's still a pure resistance of zero value. In other words, the current, the voltage is minimum, the current is maximum. Now, when we see in the phasor diagram how this works, you see, all of these theories of reflections that you had before still have to hold. So you've established one thing right now. At E max, the impedance is maximum, isn't it? At E minimum over here, what's the impedance? The impedance has to be a minimum. And that's going to be true on any standing wave pattern that you see. You will have an E max and an E min. At E max, you know that the impedance is always greater than Z0. It's a pure resistance. You know at Z minimum and E minimum, you always have a pure resistance that is less than Z0. And it's established that when the current is maximum, what's the voltage? Minimum. When the voltage is maximum, what is the current? Minimum. That's always going to be the case with a standing wave pattern. Where the voltage is maximum, the impedance is maximum. Where the current is minimum, what's going to happen here? The impedance has to be a minimum. That's where, I'm not sorry, not the current maximum, but where the voltage is minimum. Voltage minimum, the impedance is minimum. Voltage maximum, impedance is maximum. It's common sense, isn't it? Maximum impedance, you get the maximum voltage. Minimum impedance, the minimum voltage. So this is what we're dealing with when we talk about standing waves. Let's take this and apply a different look at this. But in terms of something you've seen before, but you only talked about it in terms of voltage and current. Now let's look at this from the standpoint of here is the waveform, short. What's this direction here? Toward the generator. This direction here is toward the generator. Clockwise on the chart is going to be toward the generator. On the transmission line, there are two signals traveling in opposite directions. In the textbook, if you read that chapter, there's a whole page of diagrams that shows you the two signals, one traveling to the right, one traveling to the left. After that particular page, I said that if you want to show a phasor diagram to represent that, here you have two signals, one going to this direction, one going this direction. In order to have a diagram to represent the same thing, I must fix one of those fixed in position and make the other one rotate. Right? But to get the same answer, if I stop one of them from rotating, what am I going to have to do to the other to get the same phase relationships? You will have to travel at twice the rotation. Because remember, the instant signal is rotating. It's going toward the load. The reflected signal is rotating, coming back from the load. Two signals are traveling. If I want to represent that by one vector, this vector here, E sub I, the instant signal, and I keep it fixed in position, then E sub R is this one, is rotating in this direction here. Then it's going to have to rotate at twice the angle that any one signal is traveling. Now, if you remember correctly on the transmission line, we had a distance called beta L. If the phase were 3 degrees per centimeter, and it's 10 centimeters, you'd have 3 degrees times 10 centimeters, or 30 degrees. That means that every 10 centimeters, the wave phase changes by 30 degrees. We looked at that previously on a diagram, went through it very carefully, didn't we? This is the phase constant. If you say that the phase is changing 30 degrees per centimeter, then every centimeter the phase changes by 30 degrees. Okay? So if it changes 10 degrees per centimeter, and you had 10 centimeters, 10 times 10 would be 100. It would be 100 degrees. Every 10 centimeters is 100 degrees. Because every centimeter was 10 degrees. In other words, if this is 10 degrees per centimeter, and this is 10 centimeters, right? 10 degrees per centimeter. The length is 10 centimeters. 10 times 10 is 100. And this tells you that it will change 100 degrees in 10 centimeters of travel. Okay? We've already established that. Now this beta L is in one direction. Beta, change in phase in one direction. L is the length in one direction, right? But in our case, not only do we have a wave traveling to the right, but we have a wave traveling to the left. So you're going to find very shortly by mathematical equation that this has to be 2 beta L. So this thing here has to rotate at twice the speed in order for this chart to represent this. Now notice the significance of that. If you look at this from the standpoint of this point here, this is how much of a wavelength? 1/4 of a wavelength. How many degrees is that? 90 degrees. That's from here to here. 90 degrees. Now, isn't it very simple on the chart? If this then is a short at this point, how do I know that's a short at that point? Here's E sub I to the right. If E sub R, every time I hold one of these things out too long, it dries up. If that's E sub R, what's the total at that point? E sub I and E sub R cancel, don't they? So we can see that it's short circuit, 0. All right. Now I rotate E sub R around this direction here, to the right. I'm going to rotate it, E sub R, until E sub R is over here. Now what's the total at this point? The total voltage on the transmission line. E sub I plus E sub R. Ah, very simple, isn't it? 2E. Therefore, what must this point be? Open. Notice the relationship now. How far is it from the short circuit to the maximum of 2E on the transmission line? On the transmission line? 90 degrees, right. How far is it on this chart? 180 degrees. Doesn't this hold then? That holds, doesn't it? What happens now if I take E sub R, rotate E sub R all around here, back over to here? In other words, I travel from here, back along this line to E minimum. I've traveled back to the point where these two cancel. I'm back to the short circuit again, right? So every 180 degrees, I have this, this, this. The distance from between here to here is 180 degrees, and from here to here is 180 degrees. So 180 plus 180 tells you that that is one wavelength on the transmission line. Now, notice, if I want to look at angles here, this is 90 degrees, this is 180 degrees. But you don't want to be relating angles by twice something. We want this chart here when we use it. We want to equate this chart so that whatever I say about this line is true for this. Now, I have said that this distance between here and here is how much? 1/4 of a wavelength, right? What's the distance between here and here in terms of wavelengths? Fractional wavelengths. 1/4 wavelength, isn't it? So here you see that from 0, 180 degrees travel is 0.25 wavelengths because you're traveling from here to here. 1/4 of a wavelength. When you go all the way around this chart, how far have you gone? From the maximum all the way around over to here, back to 0. So you went to the maximum and back to 0. So the chart over here represents only this 1/2, doesn't it? Then what happens? If you keep going toward the generator on here, you just keep going clockwise around the chart. So how many times around the chart will you have to go in order to go one wavelength? Twice around, right. Because each time around that chart is 1/2 wavelength. So now we have a way of equating. If I say this is 0.1 wavelengths, 0.1 wavelengths, then this be 0.1 wavelengths up here someplace. If I say this is 0.15 wavelengths, 0.15 wavelength here, 0.15 a little over here someplace. Right? This would be 0.125, which would be halfway here. So you can see that if I travel on this chart here 45 degrees, I've only gone half that distance on here, haven't I? But when I go over here to 180, I've traveled up to here. Everyone see that? Here, 90 degrees here is 45 degrees here. 180 degrees here, 9 degrees here. Now that's the way this chart is going to represent the transmission line. And every point on this chart will represent, as long as you stay on this circle here, will represent the impedance. Now let's think of this from a logical standpoint. I put this on the exam and several of you kind of missed it. I said if you terminate something in a pure inductance, how much of your voltage is reflected? Well, there's only one thing that dissipates power and knock down the voltage. Would be a resistor, wouldn't it? This is not a resistor. It's a pure reactive circuit. It's a pure inductance. Doesn't inductance dissipate power? No. So you still have total reflection with voltage, wouldn't you? It turns out then this side of the chart up here represents inductance. Therefore, what type of inductance would this be around this point here? Pure inductance. Total reflected voltage, right? Now what that means is that if I take this away, take the short circuit away, and I put the right value of pure inductance here, I didn't even change this minimum, did I? Didn't change the minimum because I just changed the position and put an inductor in here and removed the other part of the line. So this inductance here is some value out here, isn't it? Now notice, I'll travel back toward the generator from some value of inductance up here, or at this point here, travel around here, and you'll hit 2E. That's a pure inductance. What are you going to have on the other side then? When you come down here, all the way around here, the reflected voltage is total. Therefore, it's a pure reactive circuit. This is pure inductance here. If I told you that this circle represented resistance, then what value of the resistance would it have? Pure logic. If this is total inductance, this is total capacitance, what is the resistance? Has to be 0. No resistance at all, is it? No resistance at all. Because this is pure reactance, pure reactance. Now let's look at something very interesting about this distance between here and here. Suppose that I terminate this transmission line out here. Notice this is where the wave actually goes. Straight through here someplace represents E sub I. This represents the reflected voltage here, where the two are in phase, right? Suppose that I do something out in this system to eliminate E sub R. what do I have left? What do I have left? E sub I only. In other words, if I terminate the transmission line in Z sub 0, the characteristic impedance of the line, I have no reflection, right? If you have no reflection, then what happens to all this stuff up here? If I have no reflections, this E sub R is 0. That must put me at the end at this point here. Therefore, what is this point impedance-wise? What do I have on the transmission line? E sub I. So what is this point here? Z0. That's the center of the chart, isn't it? The center of the chart. What do we have over here? Open. What do we have over here? Short. Very important that you realize you are not getting away from your theory of reflections at all. You looked at them in terms of batteries and waves going down the line. Now you're looking at them in terms of sinusoidal signals. But still you are dealing with the phase of E sub R with respect to E sub I. Now notice, if E sub R is 0, this is not here. Nothing here. E sub R is 0. This puts you at the center of the chart. The only thing you would have is E sub I. If you have E sub I traveling on the transmission line, must there also be a current? What do you call that current? I sub I. This vector then, right here, represents E sub I and I sub I. Now there's a subtlety you may not think about yet. But if it's the same vector representing E sub I and E sub R, what does it say about the phase of those two with respect to each other? Simple. They're in phase, right? They're in phase. Now isn't that what we said about a wave of voltage and current that left the generator that we were talking about when we talked about the DC voltage throwing a switch and a wave traveled down the line? We said that the voltage and the current must travel together. And the incident wave going down the line, the incident wave and the reflected wave are in phase. That was defined, wasn't it? We know that when it reflects from the transmission line, that you can have other problems. Those problems being that either the signal that reflects back will be either in phase over here or out of phase or any phase in between. But we haven't discussed that in-between situation yet. Let's stick with the pure resistance part. Remember we said that if you have an impedance less than Z0, here's Z0. If it's less than Z0, is it going to be going toward an open or going toward the short? Toward the short, because it's going to be less than Z0 in this direction, because here's the short. This is in phase here. Since these two are in phase, it tells you something very definite about the impedance. That anywhere along this line, impedance-wise, is and represents only a pure resistance. But the pure resistance is always what value? Less than Z0. It will be equal to Z0 at this point. Anything from this point to this point over here is between Z0 and a short circuit. Follow this through. When you had a wave traveling down a transmission line and it hit an impedance greater than Z0, what happened? The voltage went up, didn't it? Can you see that's what's happening here? It's going to be the maximum value, isn't it? Because E sub R, if it were only this big, it would now trace out this circle. E sub R. I didn't make that as an R. But you see E sub R only goes out here. So in this case, E sub I plus E sub R is a maximum value, isn't it? Maximum value. The absolute maximum would be at the open over here where it's 2E. We know that this will always be anywhere between 2E and E, because E sub R can only vary between the value of 0 and E sub I in phase at the open. Be anywhere between 0 and E sub I, negative in this direction, meaning that the reflected voltage will cancel at a short circuit, at an open circuit, the two double. But it tells you something very interesting. We said that if we talked about resistance as a circle, that anywhere on this circle the resistance is 0. But if you talk about pure resistance, where is pure resistance going to exist on this chart? Up here. Pure resistance is only going to exist along this line. Pure R, anywhere along that line is pure resistance. Now we know then that on a transmission line, this is a pure resistance, this is a pure resistance point. We know that anywhere between this point and this point, it's inductive and resistive, or it's just inductive. Over here, it's going to be either capacitive and resistance or all capacitive, depending upon what is connected at the load. Now notice, anytime you're inside this circle, what are you going to have? Resistance and reactance. If you're on the outside of this circle, what do you have? Pure reactance. Total reflected power in the system. Now, does anyone have a problem with that? It should be very, very clear. You can always come back to this. But there's important principles you have to learn here also. I drew a standing wave pattern for you that looked like this. Voltage, voltage, that's voltage maximum, minimum, and minimum. If I looked at the current, I max, I min, I minimum. We've already established the fact that the voltage and the current are 90 degrees apart, right? Notice something about this chart. If you take the total voltage, which is the resultant of E sub I in this direction, E sub R, here's the total voltage here. The total current then is over here, this point here, and you can see the angle between the voltage and current is 90 degrees. Well, there's one thing we didn't talk about before. Why is the current vector shown as being over here? On the transmission line, the current and the voltage are how far apart? 90 degrees apart. In this case, they're 90 degrees at all times. On this chart, what are they going to be? They have to be 180 degrees out of at all time, right? Because there's twice the angle up here as there is here. Now notice on this transmission line, if it's terminated with a short, or terminated with a pure capacitance, terminated with an open, terminated with an inductance, E sub R is always equal to E sub I. You trace out this outside circle, no resistance at all, pure reactance. And in that case, the voltage and current, total voltage, total current, is always plus or minus 90 degrees. Always plus or minus 90 degrees. Now what happened when E sub R was not here? We only ended up with Z here, right? And we said before that there is also a current here, I sub I. The two are in phase, right? If the two are in phase, now what's the phase of total voltage to total current? They're both in phase, right? No phase difference. But you see it can go anywhere from 0 then, where you have only these two signals, where you have the two signals maximum, plus or minus 90 degrees. So the only phase difference, a maximum phase difference you can ever have is plus or minus 90 degrees. Notice another interesting thing. No matter what you connect to this transmission line, what's the maximum amount this minimum can shift? The maximum number of degrees this can shift. Well, if I have a short here and I put another short on, does it shift? No. If I put an open on, how much does it shift? 90 degrees, right, because I'd put the 90, open would be here. You can see that that's 90 degrees from this. The maximum it would ever shift is 90 degrees. So this shows you the angle between voltage and current. The total voltage to total current is always plus or minus 90 degrees. If you have a pure reactive load, in other words, open, short, pure inductance, or pure capacitance. It never change. Notice this. Suppose E sub R is over here. Where's E sub I? E sub I, E sub R. Now draw the total. Total voltage, total current. What's this angle here? Still 90 degrees. Okay? No matter what you do on this chart, that will always be true. There'll either be in phase, right? Or there'll be 90 degrees, plus or minus 90 degrees out of phase. Where would it be in phase? Well, if you were along this direction, right? Straight across, then there's no angle between them. But the minute you move anywhere off this line, the smallest amount, then the total voltage to the total current will always be 90 degrees. Always be plus or minus 90 degrees. That's shown here, right? Always plus or minus 90 degrees. It looks a little bit confusing, I know, but we will see a lot more of this, a lot more detail, and probably a lot better diagrams eventually. Notice that if I now normalize this to E sub I, if I divide, you remember you have E sub I plus E sub R, right? If you normalize this, you have 1 plus E sub R over E sub I, which is 1 plus gamma, right? Now, this then can also represent gamma, where this is 1. Then you have 1 plus gamma at some angle, right? Now, the angle of gamma is measured from this point. Here, the two are in phase, right? If you measure counterclockwise here, this is gamma at an angle here, angle of gamma, and you go round this direction, and it gives you the angle between the reflected and the incident voltages. Because notice, E sub I, E sub R out in this direction, they are in phase, so this must be 0. Later on you'll see this on the chart, and we'll do some actual plotting. Plot these angles of reflection coefficients so you can see it. Everyone clear on this? Any question? I think we'll take a pause here for a few minutes and then start the other tape. Okay, now let's review what we just talked about with a new diagram that has everything written on it. And I think each one of you by now have found that particular diagram in your notes. Notice that if you had a short circuit or an open circuit, that the incident voltage and incident current always are in phase on the line, right? This point between here and here then represents some impedance that is a pure resistance and less than Z0. Because this is Z0 here, the center of the chart. We know then that any time we're on this line here, along this direction, this point here, that we have a pure resistance that is greater than Z0. And notice something about this axis out here at the open circuit. We know that the voltage is maximum, the impedance is maximum. Now, when you say current is maximum, that's not maximum for an open circuit, is it? Because look, here's an open circuit. voltage is maximum, what's the current? 0. Right? But notice, if the voltage is maximum up here, where's the current? The current is minimum over here, isn't it? Go to this point here. The load is a short circuit. The voltage is 0. That puts you here. If the voltage is 0, what's the current? Maximum over here. Right? Now, if impedance is 0, what is admittance? It's a reciprocal of it, right? It's infinite. In that case, it would be where Y max be, over here. So the reason for adding these two down here are to show you that everything on the right-hand side of this chart represents a maximum value. Notice, E max here is E max here. It's also Z max, isn't it? At the same time, the current is minimum. The current's over here, isn't it? See? But now, when you go over to this point here where the voltage is minimum, you're over here. So let's label these. A. Call this one A prime. A on this chart is A prime here, right? Now at the same time, what do you have down here for the current? The current is minimum. So you'd have over here, if you called it A double prime, that's the current, isn't it? So this point here is voltage, and impedance is maximum. That's defined here. That's what this chart is. This chart is a plot of this and this together, right? Because when voltage is minimum, what's the impedance? Minimum, right? But the current is something different, isn't it? It's 180 degrees away on this chart. On this transmission line, it's 9 degrees away. So the same point on the transmission line here is this point here, voltage-wise. It's this point here, current-wise. Which says that in order for this one chart to represent that, you have to look at it that way. I could just as easily take another chart exactly like this. And then I could fold one chart out and look at it and say, that's impedance. I could close it, the other one over and say, that's admittance. But if I did that, that means that I would have a chart that showed E max and Z max here, right? When I opened the chart up to look at admittance, I'd have a maximum admittance here. In other words, this thing here would be turned exactly around the other way. You'd have two charts on top of each other. But one case, the minimum is on one side. One case, the minimum is on the other side. So if you want one chart to represent two charts, you have to think of it in terms of what's happening. E max, this point on the line. At the same time, that represents the minimum current over here. Right here. But at this point, the most important thing you want to realize is these two are together. E max and Z max. That is the defining parameter for this chart. Anytime the voltage is maximum, what's the impedance? Maximum. At the same time, forget about the current, because we're dealing with this as a voltage chart. Okay? I just want you to know where current is, because this tells you that if the voltage is maximum, the current's minimum. So if you ever have to apply it on here to see what it looks like, you know where the current is. Another reason for that is you know where admittance is, because wherever the current is, that's where the admittance is. Diametrically opposite. On the normalized chart, you'll find that's true mathematically. All right? Showed you then another thing you had here. If gamma is 1, in other words, when this is E sub I plus E sub R, normalize it to E sub I, you'd have 1 plus gamma. Gamma is 1 out here, isn't it? What do you think the voltage standing wave ratio is? We haven't gotten into that, but in the next chart we will see this and define it. And you see it's going to be the ratio of the maximum to the minimum. If max is over here and minimum is over here, then the ratio of max to minimum has to be infinite, doesn't it? All right, let's go to another chart. Any question about this? Remember that on this chart, clockwise is toward the generator. This is a zero resistance circle. The reason it's a zero resistance circle is because it's pure reactance. Okay? It's 0 here, pure reaction. At that one little point there, it's infinite. Every place else, pure reactance. Now, since everything is reflected from that, that's just an infinite impedance, but it's still total reflection, no power loss. So it's still, in effect, a reactive circuit because you don't lose any power. Let's go another step in the derivation of the chart and come up with another transmission line equation which so far we had not discussed. The voltage standing wave ratio is denoted by this symbol, sigma. Now, in the textbook, when I wrote that back in 1964, PRD and some other companies called rho the VSWR, and we used that a lot in the labs, and most people did use it. So in this text, just take a little red pencil and put, every time you see this rho, put this. That's the only difference. Now let's look at this equation. The voltage standing wave ratio is the ratio of the maximum voltage to the minimum voltage on the transmission line. E max to E minimum. Now you already know about instant reflected voltages, don't you? If the instant voltage and the reflected voltage are in phase, what do you get? The maximum possible voltage on that transmission line. E sub I plus E sub R. In other words, you have E sub I plus E sub R. When those two are in phase, you have the maximum voltage on the transmission line. When do you have the minimum voltage? When E sub R is over here, you would get the minimum voltage because it rotates around and subtracts, where they are exactly 180 degrees out of phase. We have defined that on the chart, and we will redefine it many times in the future because you'll be using that constantly from now on. E sub I plus sub E sub R gives you the maximum. E sub I minus E sub R gives you the minimum. Now, you know that if you divide this by E sub I, you get 1. Divide this by E sub I, you get 1. Divide this by E sub I, you get gamma. And this you get gamma, or you get rho as far as magnitude. So 1 plus rho over 1 minus rho, 1 plus gamma over 1 minus gamma, where you have the gamma with absolute signs around it, gives you the voltage standing wave ratio. Notice what happens here. If gamma goes to 0, what do you have? 1 plus 0 over 1 minus 0. So the VSWR can be 1.0. What does that tell you? No reflection. It says that E max is equal to E min. Now notice what happens. If I have a sine wave on a transmission line like this, and I have a probe down here, and a little crystal detector, this is going out to some meter. This wave going by this probe at the speed of light, what does the probe see? If I move the probe over here, what does it see? Or over here, or anywhere along there? It sees a wave going by it at the speed of light. One amplitude only. You move the probe anywhere along that line, do you see any change in the electric field intensity? None at all. Why don't you see a change in intensity? Because you have a maximum wave going by at the speed of light. And all it's doing is detecting that signal. No reflection, right? If there's no reflection, how many signals do you see? One. This signal is going by the probe at the speed of light. All the probe sees is just a steady stream of sine waves passing at the speed of light. And it sure can't follow a sine wave, can it? Not at that speed. Then if this is the case, the VSWR is 1.0. Why? E max, E max. E min, E min. Same value. Doesn't this show here? 1 over 1. If E max is this, if E min is that, they're both the same value. So the voltage standing wave ratio, where these two are equal, is 1.0. When is E max equal to E min? When there's only one wave going by the probe. Is there a standing wave on the line? Absolutely not. If there were a standing wave, you'd have a max and a min. And we know that only happens when you have waves traveling back and forth on the line. But if this is 0 and this is 0, are there any reflected signals? None. So when there's no reflection on the transmission line, these two signals are equal and the voltage standing wave ratio is 1. The maximum voltage is the maximum voltage is the minimum voltage. Same thing. Because all you see on the line is a probe that would go down and check the electric field intensity no matter where you move it, as long as you keep that probe the same distance from into the electric field, you see only one signal. No standing waves. Now, is that clear? We know that from everything we've looked at before. Reflection coefficient can also be expressed in terms of the standing wave. Rho, Greek letter rho, means amplitude only. You put the bars around this complex value of gamma, it's the same as this, just amplitude only, and it's VSWR minus 1 over VSWR plus 1. Now notice, if the VSWR is 1, 1 minus 1 is 0. So what's the reflection coefficient? Well, we just said that if this is 0 and this is 0, you get on 1 over 1, which is the VSWR of 1. Now it holds, doesn't it? The gamma, when VSWR is 1, 1 minus 1 is 0, this becomes 0, then the reflection coefficient is 0. We know that's true because there's no reflection, there's only one wave on this transmission line. It's the incident wave going by the probe. There is no standing wave. What does it take to make a standing wave? Two signals, same frequency, traveling in opposite directions on the transmission line. If this one is 0, this is 0, this is 0, then you have a VSWR of 1. What's the other limit? Let's suppose that this value of gamma here now goes to 1. What does that mean? Total reflection, right? Gamma equals 1. It says that E sub I, notice, if gamma is going to be equal to 1, that says that this has to be equal to this, right? The reflected signal has to equal the incident signal for gamma to be 1. Now, if gamma is 1, 1 plus 1 divided by 0 is what? Infinity, isn't it? So we know now that the range of the VSWR is from 1.0 to infinity. You already knew that the range of gamma is from 0 to 1, right? That then shows you some of the things that happen on a transmission line. Notice over here I have an open circuit. You have a pure resistance. The reciprocal of that is the pure conductance, or pure admittance over here. Pure conductance. R and G. Now, what do you have in this area between here and here? You're going to have a resistance and an inductance, unless this is 2E, which is an open. Now, I just have an arbitrary transmission line drawn up here. I have this a very sharp minimum. Later on, you'll find that that minimum is less sharp as the VSWR, voltage standing wave pattern, gets smaller. To show that, first I'd like you to look at this, though. Here's the parallel equivalent of impedance. Impedance is a series problem, remember? Admittance is a shunt problem. Remember I said that pure resistance greater than Z0? Pure resistance, E minimum, R minimum, G maximum. Okay? Here over here you have R max, G minimum, because they're reciprocals of each other. Anytime you travel on the transmission line between this minimum and this maximum, if this minimum does not go to 0, in other words, you don't have total reflection on the line, then you will have resistance and reactance in this area here. If you go at this point here, pure resistance again. Over here, anywhere from E max down to this point here, you have a resistance and a reactance. Think about something very interesting. Suppose I told you that this is 100 ohms and that this is 25 ohms. Someplace in between there, wouldn't you expect to find 50 ohms somewhere in there? Someplace in here there's going to be plus, over here, someplace in here there's going to be 50 minus jx, right? Over here, someplace between here and here, you're going to have 50 plus jx, correct? If you could find that point on the transmission line, and we're a two-wire line, and you could open it up at that point and put a capacitance in there to cancel this, what do you have left? 50 ohms, wouldn't you? Now, if you have 50 ohms, what does that tell you about the transmission line? It's matched. That's the whole theory of matching right there in a nutshell, isn't it? All you have to do is find the place on the transmission line where you have 50 ohms in here someplace. Find that place. If you find that place, open the line up and put something in, like if it were here, you'd put an inductance in here to cancel the capacitance. If you were over here, you'd put a capacitance in to get rid of the inductance. What would you have left? 50? Over here you'd have left 50. You have what you call match the transmission line, because the only thing you have left is 50. If it's a 50 ohm line, then it's matched, isn't it? So that's the whole theory of matching. Someplace then on this transmission line, if you have a standing wave pattern, you know that somewhere in between there, between Z max and Z min, is going to be Z0, right? We've already seen that. So a little later, I'll put another circle on one of these diagrams, and you'll see exactly where that 50 ohms will always be. It'll be located someplace between here and here. Not always at the same angle, obviously, but it's going to be located someplace back there, isn't it? Any question of this? Now, this is the basic definition, and this is relationship of gamma, which is the voltage reflection coefficient, and the voltage standing wave ratio. Notice I was not talking about power. I'm talking about voltage standing wave ratio. All right, let's take this another step. And I want to just show you this mathematics to give you, to make sure you don't forget what I'm talking about. Remember that when I talked about that if I said that this tells you the rate, the change of phase, 10 degrees per every centimeter is how much the phase changes. That if it traveled 10 centimeters, obviously 10 times 10 would be 100 degrees. We're going to look at something just a little different now. In transmission line theory, I know you've seen sines, cosine plus sine, cosine minus the sine. You've seen this in electronic circuit theory. Now, the reason you see the signs different here is because in this type of work, in microwave work, the reference is not the generator where the signal came from. The reference is the load. Now, notice the key to what we say is happening on the transmission line. Don't I have a voltage that's the total voltage here? I have E sub I, and I have E sub R. Because at this point, what is the total voltage? E total. The total voltage at the point on the transmission line, any point, is the incident voltage plus the reflected voltage, right? Now let's look at this from the standpoint of referring everything to here. How far is this load from this point P? Beta times L. Let's suppose that this is it, 10 centimeters beta, and it's 10 centimeters to the end of the line. 10 degrees per centimeter. So you have 10 times 10 is 100. So it's 100 degrees from here to here. 100 degrees. Now, if I'm going to reference this point here to this, I have E sub I here. If I want to reference it here, I have to say something about either where it's going to be or where it's been. If this is the reference, then this says that E sub I is here now at this instant. Where is it going to be in 100 degrees from now? It's going to be over here, right? So can't I express it that way? I can say this is E sub I, e to the J beta L, which is this function over here, which says that this voltage is here, and that it's going to be over here 100 degrees from now. You can calculate that in terms of time if you know the frequency and so forth, right? Not interested in that. We know that we are talking about the phase of signals. And we say that this E sub I is here, but here it's 100 degrees from now, it'll be over here. So it certainly has a different phase here than it'll have here, right? But when it gets over here, if this is E sub I, 1 volt here, that 1 volt will be over here 100 degrees from now. 100 degrees of travel at the speed of light. How about this signal, E sub R? It is a signal that is here now. Where was it 100 degrees before? It was over here. Now that's what this equation says. You see this? E sub R? It says that it's E sub I, R, at the load, e to the minus j beta L. What does this minus j beta L mean? It means 100 degrees from here to here. That's what this term here means. Because, notice, e to the j beta L is the cosine plus the sine, j sine. Remember what type of thing that, if you have the cosine function plus j sine function, what does that represent? It represents a rotating vector, doesn't it? A rotating vector like this. See how that's going to fit in nicely with that chart we just drew? Because what do we have? We have a rotating vector, right? This says that the rotating vector, though, is what? 1 beta L, right? What does this one say? That's the other wave. It's minus 2 beta L, right? So it's traveling also at length. If you add the two of them up, what do you get? What did we get before when we added the two? 2 beta L, right? So the mathematics shows that. Notice what this says. Here's E sub R at this point. It was over here this many degrees before. Just think of that in terms of just degrees, phase angle. This many degrees before, this signal was here, but it's here now. This many degrees from here. This wave here will be out here this many degrees later. Different phase angle, because one's going to the right, correct? One is going to the left. The one going to the left is given a minus angle. You're referring everything to the load impedance. The reference is this reference plane here. The load is the reference. Everything going back in this direction is in the negative direction, going toward the generator from the load. Okay? Now you'll find out that on the Smith chart, since it's toward the generator, what kind of rotation will that be on the chart we just looked at? Where was the generator? What was clockwise or counterclockwise? Clockwise, wasn't it? So we know that going in this direction, we're going toward the generator. We know that on the chart, that represents clockwise rotation. Notice what this says. At this point, I have this and this. But notice what the ratio is. If I look at this as E sub R, E sub I. Now notice, over here we have e to the minus j beta L. Here we have e to the plus j beta L. Right? If you take these apart, what does this give you? Gamma, reflection coefficient. Now if you take these, when you divide these, what do? Bring this up on top and change the sign. So now you'll have gamma at or just e to the minus j 2 beta L. Notice that 2 beta L? That tells you that if you have one vector like this and you have the other one on top rotating, it's going to rotate at twice the speed, and it's clockwise, because we've already shown that on the previous chart. So here you have E sub R over E sub I is gamma, the reflection coefficient. Now notice in the equations here, the total voltage is going to be the E sub I plus E sub R. E sub I, which is have this e to the minus j beta L minus this value over here. This is the true, since the sine of beta L is this two values here. Now that comes from these equations, but I remember, all I want you to know about these equations is that when you have sine plus cosine, which is e to the j beta L, is this cosine plus a sine function, which means that e to the minus 2 beta L means you have a rotating phase like this. a phase vector that is a vector that is rotating at 2 beta L. That 2 beta L represents what? Phase. In phase, out of phase. How far did it travel? From in phase, 180 degrees, right? Out of phase. We know that that represents the chart. We also know that that represents, if you looked at this as the cosine and the sine function, on the transmission line, if you look at only one of those, beta L, that represents 90 degrees. So we've got that relationship. Transmission line 90 degrees, transmission chart that represents the transmission line 180 degrees. All I'm showing is the basic mathematics. It's in the text, shows you the functions. One thing that I do want you to know is its impedance function is really a tangent function. We got the cotangent here because of the way I worked out this equation. But when you look at this in terms of the impedance, you're going to find that you have a tangent function, and you'll know exactly how that works when you look at the impedance. Because if you have a short circuit like this, you know it's going to be like this. It's going to go to a plus infinity. Then what happens? It becomes capacitive and goes from a minus infinity back up to 0 again. Because one place is inductive reactance, and on the other side it's capacitive reaction. So that's this tangent-cotangent function. Main point I want you to see about this transmission line and to know that everything I told you in a physical sense has a mathematical relationship that also holds. Didn't I say that if you had a fixed vector like this, and it's going to represent two signals going in opposite direction, all you have to do is take this one vector and rotate it, since this is a constant amplitude, rotate this other one at twice the speed. Not only that, it changes amplitude. Operate this at twice the speed, you have exactly the same result as you would have if you considered both waves traveling in opposite directions. How do you do that? The math shows that all you have to worry about is this equation here. The main part of this equation is the next one, though, which makes it a little more clear. Not if I leave that up. See, now notice, the total voltage, if you normalize this, this was E sub I, you have 1 plus E sub R over E sub I, which is gamma. Now, gamma from the load, this is the minus, this is the plus. When you add it up, you get what I showed you before. Gamma, that's a plus incidentally. 1 plus gamma at this angle. Now all that tells you is you look at this as a constant 1 is the instant voltage. Gamma is on top of that rotating at 2 beta L. That's going to be the chart. Here we have it. 1, which represents E sub I. What does this represent? E sub R. It also is gamma, isn't it? And gamma is rotating like that. What speed does this rotate in this direction, phase-wise? Minus 2 beta L. It means that every time this travels 20 degrees on here, it represents 10 degrees on the transmission line. If this travels 90 degrees on this chart, it means that it's traveled 2 beta L of 90, which is on the transmission line, is only beta L. We showed that on the previous diagram. That's what's rotating. Gamma. This value here, I'll show you what this means on the next chart. All this does is make sure that you're starting at the Z maximum axis. I can show you that that's just a mathematical equation to do that. I don't know where you would use it. I've never used it, but I can show you at least how this equation. In other words, this is the initial phase angle. Like this. Here it is. It's very easy. See this angle here between right here and here? That's this angle here. Okay? This angle here. Now what's this angle here? 2 beta L. If I subtract, now notice, 2 beta L is all the way from here over to here, right? If I subtract this one from it, all it does is put me right here at this axis, Z maximum axis. That's all that equation tells you here, is that this is starting from the Z maximum axis. Anytime you see that in the equation. remember, you're subtracting the original angle so that it puts you at Z max as a starting point for measuring all your angles. That's not what you do in a real practical world of matching and so forth. Therefore, I don't usually spend too much time except to show you what it means. The important point that you want to know is that you have this angle here. When you see, now notice what he says here, minus 2 phi. Where's that measured from? Z maximum axis. That's all that tells you. Okay? Now in matching problems, you're not going to use that. That's why I don't usually spend a lot of time worrying about that equation. But that's what it means physically. You're referencing everything to Z maximum and measuring all of your angles from Z max. Okay? In our case, we're going to be doing it a little bit different than that. You can see the equation here. This is Z max, and when you subtract these out, it always gives you this angle starting at Z max. Then if you go from Z max clockwise, it's always minus 2 phi. Okay? It's not something we're going to be using, as I said, but I want you to know what that means. This you should be familiar with. 1 plus gamma at an angle of minus 2 j beta L. All it tells you is that gamma is a rotating vector on top of an E incident, rotating at twice the speed, so that everything on the chart represents precisely what's happening on the transmission line. Now we're going to take a short break here. When we come back, we will expand this into looking at a chart and looking at these various things we've already seen, talking about the pure resistance circles and so forth. And then we're going to start talking about resistance circles and the reactance circles and what happens on the transmission line in terms of impedance being where you happen to be looking. So let's come back and take a look at it after the break. Okay, now that we've looked at the outside perimeter of this chart that we're going to develop, let's see what happens inside the chart when you have some reflection other than total reflection, which we've been considering before. We considered the limit, we considered total reflection out here, and we just, in this point here, which was Z0. And I put that up there to remind you that the center of that chart is Z sub 0. Here we're looking at a value. Here's gamma, which is, of course, also E sub r. Take your little calculators and look up this gamma that I have written up here. Gamma is 0.5 at an angle of 60 degrees. Now, if that's 60 degrees on the transmission line chart, that's still 60 degrees is the angle of the reflection coefficient. Okay? That is it. That's the angle of the reflection coefficient. What do you find for the voltage standing wave ratio of this 0.5? Same one I've told you to remember automatically all of the rest of your time in RF and microwave work. What's the voltage standing wave ratio? 3 to 1. What's the return loss? Okay. So this point here, as you said, is 3 to 1. 3.0 to 1. Voltage standing wave ratio. It's very important because we'll come back to that value a little later. Notice something interesting about this is that total voltage, total current relationship. What happened to the angle now? Even if this were up here and this were over here, this angle here is always going to be less than 90 degrees now, isn't it? Phase angle between the two is less than. Now let's look at this from the standpoint of this curve. Notice this doesn't go to 0, does it? This is not drawn to scale, but you can see this does not go to 0. Notice we have 30 degrees here on the transmission line. How many degrees is that up here? 60. If I rotate this, look at this angle here. What is this angle? Minus 2 beta L. Now notice, this point D is the same point as this D prime here on the transmission line. D prime then is an impedance other than a pure resistance, isn't it? In this case, what is the relative value here? D prime. What side is it in? The inductive side of the chart, right? So we know then that this load impedance here is a resistance in series with an inductance right here. Now notice if you go back toward the generator, you don't travel very far. As a matter of fact, you travel 30 degrees on the line, and what do you come to? Z max. Look what happens here. You go 60 degrees. What do you come to? Z max. A prime, A. You come to Z max on the transmission line. Which direction are you traveling? There's only one way you can travel from the load. That's toward the generator. If I keep traveling from A around to C, I've gone from E max, Z max, E min, Z min. Notice this. Here's A prime, all the way down to minimum, right here. Then go back, and you'd go back around the circle, back to point A again. It's a lossless transmission line. It just repeats itself, going back toward the generator. At this point here, we have a voltage standing wave ratio of 3 to 1. So we have Z max is Z0 times the VSWR. What is Z max in this case then? If we consider this as a 50 ohm transmission line, 150 ohms. That's this point here. That's the highest impedance you will ever have on the transmission line. Right here is 150 ohms. Okay? What do you have on the other side? Z min. Now notice, this is Z max. Right here. Over here is Z minimum. And that will be Z0 divided by, in this case, the VSWR is 3. So what's that going to be? 17 point something? 5 ohms or so? That's this point over here. When I said Z minimum is a pure resistance. Where? Right there. Why? There's no reactive component, just resistance. Going across the chart over here, Z maximum, pure resistance, greater than 0, Z0. That's the only 2 points on the transmission line then, Z max, Z min, and repeating itself, Z max and Z min. That's the only time you have a pure resistance on the transmission line. Because you see, that's the point where these two in phase here, EN, IN, E incident, I incident are in phase, and here the reflected voltage is in phase. The reflected current's not in phase, is it? No, because if the voltage went up, what did the current do? It went down. If the voltage went up, the current went down to its minimum value. Over here, when the voltage went down, the current went up to its maximum value. These points are located 90 degrees apart on the transmission line. Here to here, 90 degrees. 1/4 of a wavelength. 1/4 of a wavelength. Then from this point here to this point here would be from here up to here, going backwards from C back toward the load. Here, am I going back toward the load? Yeah, there's a load up here. is E minimum, E maximum, back to the load. E minimum, E maximum, back to the load. And here you have an inductance and a resistance in series. Now, if I cancel the inductance at that point, does that mean that I match the transmission line? No, it just means that I cancel the inductance. Would I necessarily make the VSWR worse or better? Might make it better. In this particular case, it would be better. You'll see that in a little later, because I'm going to show you another circle which gives you a better insight into what we're doing when we match a transmission line. But right now I want you to understand that this angle between here, measured counterclockwise from Z maximum, is the angle of reflection coefficient. Z maximum, incident voltage, reflected voltage in phase. Z max, Z min when they're out of phase. That's on the other side over here. Right? Anywhere along this line then, what do you have as far as impedance is concerned? Pure resistance. Anywhere along this line, 0 ohms, 5, 10, 15, 20, 25, 30, up to 50 ohms, if this is a coaxial line. Starting at 50 ohms, up to infinity on the other side. That's the impedance relationships, but that's the pure resistance axis. That's the point where this is a pure resistance here, pure resistance here. At no other time do you have pure resistance on that line unless the line is perfectly, absolutely matched. Then, as far as you're concerned, it's pure resistance all along the line. Any problem with this? Notice what's going to happen now. If I draw a line through here to represent E sub I, this is E sub R, like that. If at this point I come along and say, I'm going to terminate this in some other small impedance. Suppose I want to move this, I could move this point over here, right? In other words, I'm going to terminate the line now with a pure resistance, because I want you to see what happens to the minimum. Remember, the minimum on the transmission line, you have a certain wavelength, right? But what you connect to the end of the line tells you where the minimum is going to be. The first minimum is going to be located with respect to the load. Now notice this. If I do this, and I put up something greater than Z0, like this. Where did I have this? Notice what's happened here. I've put a pure resistance here, which puts me someplace in here. Okay, not out here at 150, but in here someplace. Notice what has happened. The minimum, instead of being here, is over here, isn't it? You see, I no longer am terminating this with an inductance and resistance. I'm putting a pure resistance in here. Just a pure resistance, greater than Z0. So the maximum has to appear where? At the load, the reference plane for the load. That's this point here. Now notice what happened. I didn't change the frequency, so the wavelength has to stay the same. So what happened? This minimum now moved from here over to here, didn't it? Because I terminated this line with resistors. In other words, let's say that what I actually did in this case, I removed the inductor, and that's what happened. I had nothing but pure resistance left. Well, in this case, I just terminated this with some resistance greater than Z0. But notice that the way that this minimum shifted. So the minimum located on a transmission line, if it's short circuit, the voltage minimum, like this. Open circuit, the voltage is up here, and the first minimum will be here, 90 degrees away. If you have a short here, the first minimum is 180 degrees away, isn't it? But if you have an open here, the first minimum is 90 degrees away. It'll never be more than plus or minus 90. But notice here, I took out the inductor and resistance, put a pure resistance here. The maximum shifted from here over to here. Now the minimum shifted here. And that's the waveform you would see. What happens if I put a 50 ohm load on there? 50 ohm load, what happens? In other words, is there a standing wave pattern anymore? None. Where am I? Right there. There is no standing wave. Why? Because I only have an instant voltage and an instant current. Right here. E sub I sub I, both in phase, traveling down this line at the speed of light. And I do not have any reflected wave because I terminated the transmission line in 50 ohms. There is no standing wave. No matter where I move a probe along the electric field, I get no standing waves. Now we know something about the chart. If there's no standing waves, what will the center of the chart represent as far as standing wave ratio? 1.0, right? So let's look at this and see what the chart is actually going to represent. Do you remember this equation here? I better change it around. Everybody remember that equation? You had to work it out once when I showed you what it meant just for drill, to calculate, when we were calculating impedances on a transmission line. Z max divided by Z0. Now, where does Z maximum always appear on this chart? Always. Relative. Where's Z max on this chart with respect to this point? Always to the right. Okay. So this is Z0. Anywhere in this direction is going to be Z max. Z maximum is always along that axis, isn't it? All right, let's look at this equation. Put some values in here. Let's suppose that Z max is 50 ohms. Right? What do you call this? 50 into this. Suppose I take another Z max, such as 100 ohms. One, where is this located? Right here. 1.0. Where's the 2? Out here, isn't it? Halfway out here is 0.5. What is the VSWR for 0.5? You looked it up before? Don't ever forget that. It's 3 to 1, right? That's a voltage standing wave ratio of 3.0. Right? What's going to happen then is you go out here to 300 ohms. That was 150 ohms, wasn't it? And you go out to 300 ohms, so it'll go 3, 4, 5, 6, on out to infinity, won't it? Now, when you divide every impedance out there by Z0, you say that you have normalized. You've normalized everything to Z0. Normalized. So on a normalized chart, what do you read on this axis here when you see those little numbers? 1 is at the center. What does it represent? Z max over Z0. When you read 3 out here, what does that say? 150 ohms divided by 50. In other words, the voltage standing wave ratio is 3. Now, any of you have ever used a Smith chart, and many of you have seen it on this instrumentation that you have downstairs, and maybe other instrumentation in other companies. Along this axis here, you read the VSWR. You actually read it right on the chart. This eventual chart that we're going to come up with called the Smith chart. Now, it's called the VSWR circle. This is called the VSWR circle. If I looked at this, this would be 150 ohms in this case. If I look down here, it would be 17.5 ohms. Someplace in between here, it'll hit 50 minus JX. But anyway, here you'll start out with in this case 150 ohms, then it'll go to 149 minus J something, 140 minus J, on down until it gets to a pure resistance of 17.5 ohms, I think we calculated. All the way along here then is some value of, notice if I start at Z max right here, when I go around here there will be a resistive component and a reactive component. Resistive and reactive. Resistive. Look what's happening here. The resistance is getting very small, right? And the reactance is getting small because the reactance has to go to 0, doesn't it? So the reactance will go to 0, and the only thing you'll have left is this resistance value here. And it's on the other side of Z max, isn't it? Exactly the same distance away as Z max is over here, Z min will be over here if there's no loss on the line. If there's a loss on the line, you know as you go back toward the generator, what happens to this? It would spiral in. What happens if you keep going back further and further on the lossy line? Remember what happened when we put a 3 dB pad, another 3 dB pad, another 3 dB pad on the transmission line? What happened looking into all these pads? So we have 3 dB, right? We look in here, we saw a 3-to-1 mismatch. Went out to 6 dB, 10 dB. We looked in here and saw 1.22 mismatch. More attenuation. Looking in here, you see less and less VSWR, right? Where will it eventually turn out? It'll eventually be at the center of the chart, won't it? You don't see it because there's so much isolation on the line. So you see, this still holds with that return loss theory we looked at. If you go back on the line that has losses, you can see that the VSWR just keeps getting lower and lower and lower and lower until it spirals into the center of the chart as a function of distance on a lossy line. That was the theory that I gave you in terms of actual problems of 3 dB, 3 dB, 6 dB. Okay, let's stop here just for a moment. I'll do some erasing here, and we'll do a little bit more looking into this and see some of the intricacies of this chart. Now that we have the erasures complete, we'll now look at this chart again. And remember, a lot of this is redundant, but it also has to do with the study of reflections that you had in the first 2 lectures. This is why I told you the importance of those reflections. Anytime you're at some impure resistance less than Z0, the reflected signal is out of phase. This gives you Z minimum on the transmission line, and it gives you E minimum on the transmission line. I also told you that if the reflected signal is in this direction over here, then E sub R and E sub I are both in phase to give you E max. That's also Z max. That's this point on the transmission line. Now, there shouldn't be any problem there. I told you before that this angle here, when you subtract from this angle, this is the initial line. Notice this angle. It's just the angle of the reflection coefficient, right? If you subtract that from the angle of how far you travel around, suppose I traveled all around to this point here. Then if I subtract this angle from this angle all the way around to here, you can see that it's this angle plus 180, right? That's what you would actually see. It means that if you measured this angle here, you're always starting at A and traveling around here. How much is this angle? Well, if you subtract this one out, you're starting here. All the way around is 180 degrees. So this angle here of minus 2 phi is only measured from this point here to this point here, in this case, all the way around here. So you subtracted out the original angle of the reflection coefficient of the load. That's all you did. Okay? Just a matter of keeping up with phase with respect to Z max rather than with respect to some arbitrary fractional wavelength point out here. Okay? If I go around this chart, then this is 0 fractional reflection coefficient, 0.125 up here, 0.25 out here. 1/4 wavelength on that chart. Everything on the right-hand axis is a maximum if you look at this chart. If you looked at it in terms of admittance, it's still maximum admittance, because when the admittance is maximum, at the same point on the transmission line, the impedance is a minimum over on the other side. Look at this. If the impedance is maximum, what's the admittance? Follows the same curve as current, doesn't it? Maximum voltage, minimum current. Maximum impedance, minimum admittance. At the same point on the transmission line. Are they the same point on the transmission line? If you have Z max over here, what do you have over here? Z min. But those are the same point on the transmission line. See, if here's Z max, if I tell you Z max is 150 ohms, you know the reciprocal of that would give you admittance over here, wouldn't it? 1 over 150 ohms is over here. So on the chart, maximum impedance and minimum here would mean this point right here on the transmission line. But if I want both values, I have to go 1 over here and 1 over here. Okay? I'm going to jump ahead and look at a chart here before I go back and review, because I have something here to point out and we don't want to miss. I'm not good at drawing circles on days like this, but that's supposed to be a circle. Previously, I showed you an equation, VSWR, Z max over Z0. We divided that out, and we found that if you put Z0 over Z0 equals 1, that put us at the center of the chart, didn't it? Center of the chart at this point. Now, look at this. Over here, tangent to this point. What did we say this circle was originally? If we looked at it in terms of resistance, what was its value? If we looked at it in terms of resistance, all around that circle, what did we say it was? 0 resistance. Remember that? R equals 0. What is this circle here? Every place on that circle is what? Z0. Suppose I have a circle like this. Right? It's going to be some value of R less than Z0. Why? Because it crosses wherever it crosses here, if this is 10 ohms, every place on that is 10 ohms, right? Suppose I look at this one now. We know what this one is because we've already worked at it. We said this was 3 to 1 on our previous chart. So every place on this is what? Every place on that circle is 150 ohms. Now, does it say 150 ohms pure resistance? It just says 150 ohms. Where is it a pure resistance? Where is it a pure resistance? Only on this axis, right? We already know then that we have something to work with. At any place along this axis here, there's pure resistance. That's the only place. So here, you have a circle, 150 ohms. It's only 150 ohms pure resistance right there. Here you have a resistor circle. Every place on that circle is 50 ohms. If this is Z0, it's 50 ohms. But this one is the only point that's a pure resistance, right where it crosses the pure resistance axis. That has to be along here. Notice, this one crosses right here. Now there's a number there, isn't there? If you take that number and multiply it times Z0, what are you going to get? The value of the resistance. If you multiply this 1.0 times Z0, what do you get? Z0, 50 ohms, if it's a 50 ohm line. Now something very interesting on this transmission line. We know that in this case, this is 150 ohms right here, right? We know that over here was 17.5 ohms. Someplace in between, what are you going to have? Some fractional wavelength over here. L over lambda, if you want to call it that. But notice this point here. What do you have here? 50 plus JX. What do you have over here? See? Now one of these, let's just say that one of them just happens to be here, right at the load. The other one is over here. One is here. Now this one is right here. Okay? This point is the one up here. Over here's going to be another one. What do you have on this point here? 50 plus JX. What do you have over here? 50 minus JX. Right? Now first of all, let's talk about impedance, which is a series problem. Are you going to work series problems inside of a coax or waveguide? No. Two-wire line? Possibly. Because if it's a series problem, if I want to put an inductance in series to cancel a capacitance, what do I have to do to the line? Open it up, right? And put something in it. You're sure not going to do that with coax. So you know that when you start working inside of coax and waveguides, you're going to be working really with a shunt problem, which is admittance. But I'm going to explain this right now in terms of impedance so you know what we talk about impedance matching. But think of this in terms of a two-wire line that I can actually physically open and put something in series with the line. Two-wire line. Notice this. If this point here happened to be this point here, then at that point where the load is, if I can open up, take the load off, and put in a value of capacitive reactance in series with that load right at that point to cancel the inductive reactance, what do I have left? 50 ohms, right? Let's say that this is, Jesus Christ. That's the actual load. If I can take this load off, put a capacitive reactance of minus JX in here and cancel that, what do I have left? 50 ohms, right? Where does that put me on this chart? Right there, correct? All right, let's go back along the line. See, I'm over here, right? That happened to be this point here. Now I'm going to travel around this transmission line. This is a fractional wavelength, some L over lambda. I travel from here all the way around to here, which is from here over to here. This distance here is from here all the way around the transmission line to this point here. Still running out of red ink, I guess. Notice it crosses right here at this point. Here, instead of having 50 plus JX, I have 50 minus JX. Right here, it's capacitive, isn't it? Now suppose I take this two-wire line and open it up, and I put a plus JX in there. What do I have left? 50, right? Where would that move me? Back to the center of the chart. What would this look like on the transmission line now? What would I see if I put the JX in? I would see no standing wave, right? I would see this. No standing wave. because I've moved back to the center of the chart. You still have the standing wave pattern in here, don't you? It is a little different than the way it looks there because it's been redistributed so that all the power that goes past this point is dissipated in this 50 ohms resistor here, regardless of what this is. But now you see you still have a pattern in here, but looking in here you wouldn't see that, would you? When you put this in here then to cancel this, what you've actually done is directed all the power to be dissipated in the 50 ohms. You've redistributed the relationship of voltage to current so that all the power is lost in the 50 ohms. That's all you've done. Look at this in terms of a slide screw tuner. Slide screw tuner is a waveguide device that has a metal probe that can go down in the guide like this, but it can be moved in either direction. Now notice, this is a shunt problem, right? In other words, looking at this like this, this really is this point over here. Now I travel along this transmission line until I get over to here. Here, around to this point here, see, which is how far I would have to travel. In this case, it's exactly 180 degrees, isn't it? Just so happens that I chose it that way. So after I go around 180 degrees at this point here, you see, then I can match the transmission line. So what actually happens inside this structure like this? You have a probe. What's the mismatch here? 3 to 1. Right? If I put this probe in here, move it along the line, and I look in here with a slotted line. In other words, I have another probe in here. I can move this probe back and forth, and I adjust this one until this is gone, and the only thing I see left is I move the probe along the line. This probe here. I move this probe along the line. It's in what's called a slotted line. I move this probe back and forth, and I keep adjusting this probe depth and along the line until here I see nothing except a straight line. That's how you actually match. We'll do that here in the classroom later, a few lectures from now, because we're going to put a system up and you'll get a chance to try your luck at this. If I move this back and forth until I don't see any wave coming back out of here, I see no power coming back. That means I have no standing wave. Right? No standing wave. I match the transmission line. If I took this away now, took this disconnected here and put a perfect load on here and measured the VSWR in here, what do you think I would see for this problem here? Well, in order to cancel this 3 to 1 mismatch, you have to put a 3 to 1 mismatch in here. And you phase it along the line. And all you're doing is phasing it so you direct all of the power down to the end of the line. You can think of that like you do an antenna. When you put those little put your little directive array out here, you put them a certain distance apart so you direct all of the transmitted power in one direction, don't you? Well, you're doing the same thing here, except you're changing the phase relationship so that all the power is dissipated across this resistor out here. But to do that, you find that it takes a 1.1 mismatch to cancel a 1.1. It takes a 2.0 to cancel a 2.0. You already know that. 3 to 1 to cancel a 3 to 1. If I cancel out plus JX, what do I cancel it out with? Minus JX. So there's two ways of looking at this. One is, where does the power go? And the other is from a circuit element standpoint. Minus JX cancels plus JX. Power-wise, you're directing the power. You're phasing it so that the power goes in one direction. One thing is pretty definite, though, is it takes a 1.1 to cancel a 1.1. Takes a 2.0 to cancel a 2.0, and so forth. Now you see the basic idea of matching. The places you can match a transmission line are only on that Z0 circle. That's the only place you can match it. So when you're doing this physically with the circuit elements, that's the only way it could be done. Let's go back then. Look at this one more time easily and slowly, because you cannot forget this. Incident signal, reflected signal. Incident signal, this represents gamma. the reflection coefficient. The angle between the Z max can be measured counterclockwise from Z max is going to give you the reflection coefficient angle right here. This is 0, measured counterclockwise here. You get over here, it'll be 180. Now you know that if you put a short circuit on a transmission line, that the phase of the reflected signal is exactly 180 degrees out of phase. That's what this chart shows. It starts at 0 degrees at a maximum, and it goes to a minus 180 over here at the other side. Okay? If it's a short circuit, the gamma is 1. If it's anything other than that, in this case here, we had the gamma of about 0.5, which is the way I drew most of these. So here you have going from A. If you go from A to B over here, you go to Z max, A prime to B prime. Chart, twice the angle of this angle here. You went from an inductive and resistance value to a pure resistance value here. Then you go all around the line here, and you'll have in this area, here's D. In other words, you've gone along the line here, back around here, just around the chart. And you have a resistor and a capacitor at this point here. Go back here, you have pure resistance, Z min. If you travel this way, clockwise, you're always going toward the generator. Back here, counterclockwise, you're going toward the load. Now, it's very interesting about this particular indication, because if I have a load here, and I tell you, the first minimum is located 200 degrees from the load. How do you find the load? You see, I give you the key. I say the first minimum is 200 degrees from the load. All right, here's the first minimum, right? How many degrees away from the load? 200 degrees. How do you find the load? You got to go toward the load, right? Which is this direction, which means that here's the minimum. I would go around here 200 degrees, and lo and behold, I'd find the load over here. So remember, it all depends on how you define this from an academic standpoint if you're working problems. If I give you a problem, I'll tell you the first minimum is located so far in the front of the load. If I do that, you know that the first minimum is here. Suppose I told you the second minimum. I could say the second minimum is 702 degrees. See? You'd start here and you'd go around and around this chart until you get that many degrees. Knowing that around the chart one time, half wavelength. Around it again would be another half wavelength. So you guys got to keep that in mind when you work problems. But you see, it's going to be simple because the numbers are on the chart. Okay? Told you that this circle here is called what circle? When you talk about it, and when it's discussed or tells you to draw that circle, it's called the VSWR circle. It's convenient because along this axis on the chart you find that you read the VSWR because it's right there in numbers. Could I also call this the gamma circle? Why not? Because gamma is a radial scale parameter, isn't it? Could I call it the return loss circle? Yes, because every point on there is uniquely related to the VSWR, isn't it? So really, this circle represents any propagation characteristic. Return loss, mismatch loss, reflected power in percent, gamma, and the voltage standing wave ratio. All of those parameters really are and can be looked upon as the circle because it's the same magnitude. There are other circles on here which we're not going to get into today, but they start over here and they'll come out like this. Those will be the reactance circles. You'll have the resistance circles. Any place a reactance circle and the resistance circle cross, you can read the two values right on the chart. We'll be doing that, and you'll be actually working problems. And when we do some impedance measurements in practice right here in the classroom, you will be required to plot these impedance values on the Smith chart. Relatively speaking then, going toward the generator. If you have an inductive load, you can see it. First thing you'll come to is Emax over here. Keep going around the chart, you will come to the minimum. Keep going around, you'll go back to the next maximum. Keep going around again, you'll come to any particular value over here. All of this is very plain and easy to see here. Now here's the value of conductance, R over R squared plus X squared. The susceptance is X over R squared plus X squared. That's these values here. That's the parallel equivalent of this. In waveguide and coax, you happen to work with an admittance problem because it's a shunt problem. When you do matching, you would actually do the matching according to this. And we're not going to be doing that because when you do that and you have to design the particular structure to match, then you run into a real problem, academic problem. When we talk about components, you'll see what those components look like. And designing them is not an easy job. Each one of you I believe you have this in the book. If this represents E sub I, what does this vector, what does this phasor signal right here represent? E sub R, right. If this is normalized so that E sub I is 1, what does this represent then? Gamma. Everyone see that? This is a unit input voltage. Then the reflected signal can only be between 0 and 1, right? 0 and 1. It can be anywhere between 0 and E sub R equal to E sub I, if you're talking about instant reflected voltages. The angle between here and here is the angle of the reflection coefficient. And it tells you that if the two signals are in phase out here, then you would have a pure resistance on the Z maximum axis. One thing about this chart, everything on this, that's the maximum axis, isn't it? Everything on this side is the minimum axis. If you were talking about current on this chart, the current maximum would always be over here because the voltage minimum at the same point on the transmission line would be over here. Okay? What's the center of the chart here? Well, if it's 1, that means you've normalized it. But we know that that center of the chart represents the characteristic impedance of the transmission line. So that's enough for that particular diagram. Anytime you're inside this circle, we know what this circle out here is. That's 0 resistance. Any circle that goes out here and crosses this axis over here between here and Z0, it's going to be some value of resistance, pure resistance, less than Z0. But any place on the circle, of course, like this, any place on that circle we'll say is 12 ohms. But it's only 12 ohms pure resistance right there. Okay? I don't think you have any problem with that. If I have this circle drawn here then, whoop. That would be called the Z0 circle. Every point on that circle is 50 ohms. But if it's any point other than this, it'll either have an inductive component or a capacitive component. But that's it. The 50 ohm circle. For this particular transmission line, I can only match it here and here. In other words, if I go from the load, this is the load. If I go from the load just a short distance, you see, just a short distance here, I can match the transmission line right there. Otherwise, I have to go all the way around and match it over here, which means going from from here back over here on the other side someplace to match it. So that's the way it works. Suppose I have a circle like this. What's this value here? A pure resistance value greater than Z0. If this represented 800 ohms, every place on that would be 800 ohms. But it's only 800 ohms pure resistance right here on this axis right here where it crosses. Okay? 800 ohms, how much, what would the VSWR be? 50 to 1, pretty high, right? Okay. This will be convenient for working some problems out later on. Here's the same type of graph here. This represents total voltage to total current. Total current. The angle between the two will always be less than plus or minus 90 degrees as long as you're inside this circle. Again, this circle is called the VSWR circle, but it really represents all of your radial scales because it's constant return loss. But if you read this, you know that at the maximum, later on you're going to find that you have